Hi guys, we're going to continue on talking about the isoelectronic ions, and I want to do that because the bell rang and we didn't give it, I think, as much justice as what I would have liked to have given it, and we only have a few slides that we didn't get through, so ionization energy and electron affinity, so that's what this video is going to be about. And then I also already made yesterday your videos for today, so unfortunately you have just a little bit more work than what I would have liked us to have. So just kind of bear with me with that, okay? Hopefully we won't have this much video ever again. Okay, so isoelectronic ions, remember we know iso means same, electronic is referencing electrons, so a same number of electrons. We particularly looked at these group of isoelectronic ions, or isoelectronic atoms. I have my oxide ion, fluoride ion, neon, sodium ion, and magnesium ion. And today in class, we broke down and said, this was my proton count, this was my electron count. So they're isoelectronic because they all have the same numbers of electrons. Let's write their electron configuration, because if they all have the same number of electrons, then that means that their electronic configuration should also be the same. So let's just check. If I were to write the electron configuration for neutral oxygen, not the oxide ion, it would be 1s2, 2s2, 2p4. So that would be neutral oxygen. But I don't have neutral oxygen up here, I have the oxide ion, so I have 2 additional electrons that oxygen has gained. So instead of this being 4, it's now going to be 6. Okay, so this is my electron configuration for the oxide ion. Let's do the same thing for fluorine. So for fluorine, if it's neutral, is 1s2, 2s2, 2p5. Now, fluorine has gained an additional electron. So instead of 2p5, it's now going to become 2p6. So right now I'm seeing that both of these have the same electron configuration. What if and we know neon has this, but now if I go to sodium, let's look at sodiums. So for sodium, it would be 1s2, 2s2, 2p6, 3p1. Now sodium is a cation, meaning that it would more readily lose an electron, because if it loses one electron, then that means that it will have that full outer shell, and that will create that stability that it wants. So which one am I going to get rid of? I'm going to get rid of this outermost valence electron here, which is the 3s electron. And if I do that, I'm now left with that electron configuration. So I see that isoelectronic ions have equal number of electrons, thus meaning that they're going to have the same electron configuration, okay? But if I want to think about also now their effective nuclear charge, if this is the electron configuration that all of the 5 ions up here have, then what is technically now my outer, what are my valence electrons here, what are my core electrons here? So I would go from the previous noble gas. So really that noble gas that I would be looking at would be the 1s2, and that would be my helium, so then that would be my core electrons. So if I wanted to write noble gas configuration, I would do helium, and then I would do 2s2, 2p6. Okay, so now if I think about effective nuclear charge, let's go there, and I wanted to calculate effective nuclear charge. And actually, let's erase this one too. So I want to calculate effective nuclear charge. To do that, remember, it is Z minus S, and we said that Z is the number of protons or atomic number. So protons minus S, which was that shielding constant, and we said that really that's just the core electrons. So if I want to find my, let's just go ahead and make a new row here. If I want to find my effective nuclear charge, then here I would do protons minus the core electrons. All of these will have a core electron of 2, right? Because I would have 2 electrons there for helium, so I should technically have 2. So here I would have 8 minus 2, and then fluorine would be 9 minus 2, and then neon would be 10 minus 2, 11 minus 2, 12 minus 2. Okay, so I see that as I'm going this way, my effective charge is getting larger. And I asked you today in class, how would I arrange these if I gave you all 5 of these particular elements or ions? I want you to arrange them from smallest radius to largest radius. It would actually be flipped the way that I have it written. So the smallest radius would be the magnesium 2+ ion, and the largest radius would be the oxygen 2- or the oxide ion. And that's because magnesium has the biggest effective nuclear charge here, which means that it's going to pull those electrons in really tightly towards the nucleus because there's a greater Coulombic attraction with the same amount of space for the rest of these. So magnesium is going to be the smallest, followed by this, followed by my neutral. Fluorine will be bigger because now I've added another electron, so not as much pull, weaker Coulombic attraction. And then I can also say that the effective nuclear charge is not as great as the ones that were smaller. And then oxygen, of course, smallest effective nuclear charge and probably less Coulombic attraction than as well because now I've added another electron. So because of that, it will be the largest, okay? So that's just talking about isoelectronic ions and looking at their electron configuration as well as that effective nuclear charge. So if you have any questions about this, let me know, but we're going to continue on. And actually, we want to get into ionization energy. So what is ionization energy? Well, ionization energy is the amount of energy that it's going to take that I need to apply to an atom to remove an electron from the ground state of a gaseous atom or ion. Okay? Ionization energy, amount of energy that it's going to take to remove one electron. These are going to be in successive order. So that means I'm going to remove one electron first, and then I can remove another one. So actually, there's a first ionization energy, there's a second ionization energy, a third, a fourth, a fifth. So the first ionization energy just means how much energy it requires to remove one electron. Second ionization energy, the energy it's going to take to remove that second outermost electron. Third electron, so on and so forth. So think about them like the polyprotic acids that we talked about. They come off stepwise, the hydrogens do. Ionization energy will be the same way. We're going to take an electron off, one electron off at a time. So if I want to show this, if I want to show a reaction in terms of ionization energy, then you're going to see it written this way. So I have sodium in a gaseous form, and ultimately I'm going to give it enough energy so that I can get an ion, and then I can get rid of one of those electrons. So when I remove an electron, I'm going to form an ion. We already know that. So if I want to somehow symbolically show ionization energy as a reaction, we're going to do it this way. So this is the first ionization energy of sodium. And then the second ionization energy in terms of a symbolic reaction would be the one below. So here I have the sodium ion in gaseous form. And then if I remove another electron, I'm going to get Na2+, okay? This is probably going to be more like what you're going to see on the AP chemistry test. So you'll have some type of chart like this, and a lot of times they like this just because we can see what's happening in terms of ionization energy jumps for valence electrons versus those inner core electrons. So for example, let's just focus here on sodium. And I'm sure that's so hard for you to see probably on this video screen. No, I think maybe you can. Okay. So I have sodium here, and right now I've only written down or shown 2 ionization energy levels. So I have the first ionization energy is about 496 kilojoules. Probably per mole. Yep, kilojoules per mole. Okay, so first amount of energy to remove the first electron, that outer valence electron of sodium, it's going to take 496 kilojoules. That's really not a lot of energy in comparison to just me looking at the rest of this chart, which are in like the thousands. It's not a lot of energy. And if we think about that logically, it should make sense to us that sodium would prefer to get rid of that outermost electron. So because of that, it should have a really low first ionization energy. And that's exactly what I see. So far, logic is winning. We're good. Now let's go to the second ionization energy of sodium.